Today, on How It's Made. Golf balls. Getting into the swing of things. Furniture handles. We had to use some pull to get into this factory. Parking meters. Before time's up, you'll see how they make them. And room dividers. We bring you wall-to-wall coverage. Different types of golf balls deliver different results. Highly skilled golfers often use what's called a wound ball, a ball made of rubber thread wound tightly over a core because its flight is more controllable. But most people use what's called a two-piece ball, a ball whose core is covered in a dimpled material. Today's golf ball has really come a long way if you consider that the early ones were made of feathers. This is what's inside now, a bouncy rubber. They mix it up with other chemicals to make a hot batter, and then roll it out like a pie crust, cooling it between two huge steel drums. Next, they push the rolled-up rubbery sheets into this machine called an extruder. There's a ram inside and it forces the rubber through a die. This makes shapes that resemble large marshmallows called slugs. A conveyor belt sends them to a compression mold machine. Here, a worker positions the slugs in a steel mold. The slugs often vary in color depending on the type of ball being produced. When the door closes, the bottom part of the mold presses up into the top part, applying over a ton of pressure. This is a shape and bake system, because inside this mold, the newly rounded rubber is cooking at 167 degrees Celsius. Baking it for 13 minutes hardens it. Then, after it's cooled with water, a worker places a piece of slotted plexiglass over the mold. This holds down the leftover trimmings so that only the ball shapes get picked up by the vacuum. He peels off the excess rubber for recycling later. The marshmallow-shaped slugs have now been transformed into a solid golf ball core. A robot transports these cores to another mold. A ram pushes melted plastic through tubes and into a mold cavity. This forms the outside shell of the golf ball, complete with the dimples that will help the ball travel farther. This is an inside look at a ball with its new shell. This injection molding system generates 4 dozen golf balls every minute. The new balls are on the move. They roll into a bin which funnels them to a golf ball elevator. They're on their way to get cleaned up. Look closely and you'll see little pieces of leftover plastic on the ball shells. The next process will get rid of that. This is an automatic miller that removes the excess plastic. This is a golf ball before milling. And here it is after the flecks of plastic have been removed. Next, robotic arms shuttle the golf balls toward a chute entry. This is a quality checkpoint. If the ball is not smooth and uniform, it won't go through this hole. Now, a wheel rolls the golf balls towards a stamping machine. Robotic arms carry silicone pads to an etched steel plate. The pads soak up ink from the etched plate and transfer it to the balls. The pads brand each ball with a player number, the company name, and the model type. Then beams of ultraviolet light harden the ink. They dump the balls into a bin, but they funnel some balls over to another stamping machine. This one does custom logoing. Now that's a stamp of approval. Next, an automated machine sprays the balls with polyurethane while they rotate atop spindles. The polyurethane protects the ink logos that have been stamped on the balls. Robotic arms carry the wet golf balls to a drying rack where they cook at 66 degrees Celsius for 5 minutes. Then they're done. And that's the technique behind the golf ball. It's up to you to explain your golf technique. Imagine a dresser with antique-style brass pulls. Now imagine that same dresser with country-style wooden knobs, or funky plastic knobs, or sleek handles in stainless steel. The decorative hardware on a piece of furniture or on cabinetry dramatically affects its look. So changing it is an easy and inexpensive makeover. How would we get a grip on things without knobs and handles? But they're more than something that can open doors for you. The many styles add to the appeal of our furniture. To make a handle, an electrical hoist drops big chunks of zinc into a melting furnace. At 427 degrees Celsius, metal quickly turns into liquid. It's so hot you'd lose a finger if you touched it. Automated arms move an iron pot full of the liquid to a railroad car which takes it to the next stage. Here they pour the liquid metal into another furnace that's just as hot. This is called a machine furnace. A hydraulically driven cylinder pushes the liquid metal through a system of nozzles and pipes that run through the furnace. It carries the liquid metal to a die. The die shapes the handles cookie cutter style. Water flushes through the die. This cools down the zinc and it hardens into a handle shape with a lot of extra molding that they're going to have to get rid of. So now that they've cooled, it's safe to touch them and remove some of that waste. A worker snaps some of it off and tosses it in a bin for recycling later. And the handle shapes go into a separate bin. But there are still some little bits of waste on the handles called overflows. So a mechanically driven spinner tosses the handles around and knocks off any overflows that have been missed. It's a lot faster than picking off those little pieces by hand. A worker dumps the handle shapes into a bin. They're starting to look like something you could really hang on to. A similar die casting system is used to make knobs, but the knobs come in two interlocking pieces. They place them on a turntable and fit them together. Then a 4-ton hydraulic press presses down on the knob, and that pressure seals them. They pour a mixture of water and oil on the knobs to cool and lubricate them, while an automated machine drives a screw into the back of the knob. This makes a thread pattern inside of it, so it can be easily screwed onto furniture later. Now they plunge the handles into a chemical bath. The chemicals help to conduct electricity. This process is called electroplating. The handles are negatively charged. The brass particles in the water are positively charged. They attract and connect, and this causes the brass plating to form. They dip the handles into the chemical wash twice and then rinse twice. Next, they dump the brass handles into a vat of acid. This oxidizes it, blackening the finish to make it look antiqued. This brass pull has aged 100 years in just a few minutes. Next, they funnel the handles into a big round polisher. It's called a bowl vibrator. The handles are mixed in with steel ball bearings. The machine vibrates and the friction from the ball bearings polishes the handles. Now those antiqued brass handles have a shinier finish. Sometimes they use ceramic pellets in the polisher instead of ball bearings. They spray soap and water into the bowl to lubricate the handles and allow them to move freely. This gentler friction results in a different finish. The polish on the handles will be brighter. Now they put a handle into a clamp. With air pressure, it puts the squeeze on the handle so that it hooks into a back plate. When the pressure is released, the fit is snug. A front and back plate gives a handle a more elaborate look. They buff up a knob with a cloth polishing wheel that's mechanically driven. This process gives knobs and handles a certain gleam. It's the finishing touch. So now you have a handle on how furniture hardware is made. The Beatles wrote a song about lovely Rita, the meter maid. But try finding anyone else singing the praises of those uniformed patrols who ticket your car when your meter expires. Parking meters have been around since the 1930s, and ever since then, drivers, especially those caught without change, have been cursing them. It's time to unlock the mysteries of the parking meter and find out just what makes it tick. First, the low-tech part. The time limit label goes onto a zinc dome-shaped plate. Then a worker sprays lubricant onto various parts of the motherboard that contains computer circuitry. After he snaps the board onto the plate, he screws it in. Then he fastens another dome-shaped plate onto the back, sandwiching the motherboard between the two plates. The worker hooks the board up to the power source, the battery pack. And he tucks the pack into a special compartment so that it's secure. Then he plugs a programming device called an X key into prongs protruding from the motherboard. The key feeds software to the motherboard inside. When numbers appear on the screen, it's programmed. The next piece, called a smart chute, also has computer circuitry. It analyzes the coins as they fall through the meter. It can tell the difference between Canadian coins and American ones, and even recognize coins from other countries. He puts the chute into a protective plastic casing and plugs it into the protruding prongs that were used earlier to program the meter. The two boards make a connection and can now communicate to one another. He clicks another zinc plate over the coin chute and adds a stainless steel coin slot for added protection. This card is a radio frequency probe that detects how much money is in the meter as well as maintenance information. Just how good is this meter at analyzing coins? Well, a Canadian nickel and a British 20 pence are roughly the same size. Put in a Canadian nickel and you get 3 minutes. But try the 20 pence. Nothing registers. The meter treats it like a plugged nickel. The meters are now in an environmental chamber. This chamber replicates the most extreme climate conditions. It's a test to make sure they're ready for life on the street. Now it's time to make a lock. He puts a zinc alloy lock plug containing brass tumblers into a miniature lathe. The lathe spins rapidly on its axis while pressing against hard steel blades. The blades cut the spinning lock tumblers to the appropriate length. The result? A lock plug that has brass tumblers of different lengths that can't be opened without the correct key. Here, a worker places the lock barrel in a vise to give a better view of the lock system. As you can see, it turns easily with the key. But vandals beware, this lock is designed to be tough to pick. Next, he inserts the lock into the bottom of a coin can that's made of plastic. He closes it and then puts it on what's called a sonic welding machine. It emits high-frequency sound vibrations that actually melt the rigid plastic, welding the top and bottom pieces together. Now these coins will be really tough to get out without that key. Next, he brushes a second lock system with a lubricant and adds a hard steel shield that will resist attempts to drill into it. This lock goes onto an iron door which will be part of the vault that contains the coin can. He brushes the lock assembly with another lubricant to make the locking operation smoother. Then he installs a rubber gasket along the frame for the meter dome window. This gasket seals the dome and protects the electronics from harsh weather. He places a tough plastic window on the gasket and tops it with a zinc strap. He screws all the pieces together. Then he places the iron case that will hold all the mechanics on top of the vault containing the coin can. He attaches the windowed cap and strap assembly with hinges. And there's a third lock to help protect the electrical components of the parking meter. After a check for fit and function, he installs the actual mechanics. This means it's all systems go. The parking meter is ready for the street. Later, the coins can be collected without even opening the plastic coin can. This special receptacle activates the lock at the bottom of the can. Once turned, the coins deposited into the parking meter drop into the receptacle. If you need to section off part of a room, there are many types of room dividers that can do the job. Accordion doors routinely divide meeting rooms. Sliding walls made up of multiple panels can easily split a large reception hall in half, or partition an office in no time at all. This particular company makes two types of room dividers: sliding panels called operable walls and accordion doors. Both have built-in soundproofing. The folding mechanism at the core of an accordion door is called a pantograph. It's made of flat steel bars riveted together in a crisscross configuration. A worker tightens the rivets just enough to hold the bars in position without impeding their movement. Then he inserts pins along the top and bottom, securing them with steel retaining rings. The pantograph is custom built to expand to the precise width of the door they're making. The pins attach to the covers that will later sandwich the pantograph, forming the accordion door's surface. To make those covers, they first make slats. This automated machine hot glues a band of cardboard onto a band of steel. Then a series of rollers progressively folds the sides upward, forming a steel edge around the cardboard. Finally, the machine cuts the continuous band into slats, whose length is the height of the accordion door they're making. Now workers pair up the slats, connecting them with cardboard strips. They feed each pair into a glue machine. The slats come out adhered to a soft and flexible type of paper that's tear-proof. Next, workers connect 6 pairs of slats to form a panel. Then they glue on the decorative surface, in this case, commercial quality vinyl. To block sound from passing through the space above and below the accordion door, a worker glues a felt and vinyl strip to the top and bottom of each panel. After lining the inside of each panel with acoustic wool, a soundproofing material, a worker gathers the number of panels required for the door's width. He attaches them using industrial-strength steel staples. Then he slips U-shaped steel channels onto what will be the door's inside folds. Using an air-powered machine called a serter, he presses the channels tightly in place. Now he installs the pantographs. The height of the door determines how many. Using steel retaining rings, he locks the pantograph pins into holes on the channels. The second cover goes on the same way. After this, workers apply a metal trim to finish off the front and back ends. They also install a handle for opening and closing the door. The door hangs by wheels attached to the top pantograph. Operable walls are made up of several sliding panels. For each one, workers build an aluminum frame, then install a soundproofing mechanism, a crank-activated aluminum seal that juts out to fill the gap above and below the panel. To make the front and back faces of each panel, workers begin with a sheet of gypsum board. To one side of it, they glue a steel sheet that's at least 1 millimeter thick. This provides soundproofing. To the other side, they glue a decorative surface, in this case laminate, a thinner version of the material used for countertops. A machine called a pinch roll applies pressure to ensure the laminate adheres well. Workers slide the face into the frame, fill the middle with acoustical wool for soundproofing, then slide in a second facing. They close up the bottom, then test the retractable soundproofing seal. The last step is to install the wheels that run along a ceiling rail. An operable wall can have one or many types of faces, from fabric, mirror, or galvanized steel to blackboard, marker board, or even cork bulletin board. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.